Thank you. Our speaker this morning is Dr. Priyanka Nagar. She studied at the University of Pretoria, where she obtained her BSc in Actuarial Science and Financial Mathematics, her MSc, and then her PhD in Mathematical Statistics. Her research interests are in the field of directional statistics with various applications. Her PhD thesis focused on applications in wind energy and orthopedics. From 2017 to 2020, Priyanka was appointed as lecturer in the Department of Statistics at the University of Pretoria. In 2021, she moved out of academia to work in telecommunications industry as a data scientist. And in 2022, she rejoined the University of Pretoria in the Department of Statistics. And she is now currently at the University of Stellenbosch. We welcome Priyanka today to talk about her research on modeling multivariate biomechanical data with the circular linear model. Thank you.
Thank you, Bruce. Thank you everyone for joining me this morning. My talk today is based on a paper that was recently published in the Journal of Statistical Methods in Medical Research. And this is joint work with Professor Andrea Bakker from the University of Pretoria, Professor Mohammed Rashi from the University of Mashhad, and then Dr. Korjakas Hikat from the University of Pretoria as well, and then Dr. Annette Christie Barnard from the Walker Mile Center. Okay. So the outline for my talk today is the motivation for the study stems from the biomechanical domain. And as such, we're just going to start by setting the scene and giving some background into where the problem originated and what the motivation for this application is. We'll then go into where the research questions come in, and then look at some of the tools required in order to answer these questions, and then the proposed methodology. So how do we build up this model that we're going to consider for the application? And we'll also look at some final remarks. Okay. So the biomechanical domain. There are many different types of applications within this domain. What we're going to be focusing on is a device or an instrument called an external fixator. An external fixator is a medical instrument that is made use of when we experience a fracture or heavy damage to a bone. So if you think of a bone breaking, or there's a fracture at a site and it forces someone to be immobilized because they can't make use of that bone. So if we think of, for example, the leg, and you have your tibia bones upon your calf, if there's a fracture on that area, the best way in which that fracture can heal is by immobilizing the bone and placing this device, fixing it onto the leg so that it can allow the healing to take place of the bone fracture. Now, the healing of the fracture is dependent on the amount of strain. So you can imagine that even if you get an injury, the more strain you insert around the injured area, the longer it's going to take for that fracture or that injury to heal. The idea behind an external fixator is that it immobilizes the area where there's a fracture to the point where it allows for some motion, but restricts most of the motion. And we would like to optimize the healing time with these devices, as they are extremely expensive and extremely heavy. And you can imagine that having this device fixed on a person can be very uncomfortable as well. These devices are usually constructed with a combination of different materials, so metals and rings and pins and rods and wires. There are different ways in which these elements are combined to create a specific type of device. And we're going to look in this study on on a specific configuration or manufacturing company that constructs an external device, which we'll have a look at on the next slide. There's an image of what it looks like and what type of configuration in terms of the rings and pins are considered. Now, with these devices as well, one of the main interests is the stability of the construction. So since there are different ways in which all these little elements of the device can be combined, we want to test how stable is a specific configuration based on another configuration, as well as different manufacturers. And the way in which we analyze the stability of the device is by considering the amount of displacement that the device allows for. So the displacement is a motion regarding the positioning of two ends within this fracture. So the proximal and the distal ends, we consider movement within these two areas as a quantity that we can use to describe the stability. So how does this device actually look? On the left over here, we have an image of the physical device itself. So this is one specific configuration that we have considered within the study. And we can see that we have these metal rings and these rods that are connected. And there's also some pins over here that are used to fix the device onto the area around which it's around the fracture area. Okay. Surprisingly, this device is extremely heavy. We were fortunate enough during the course of the study to actually physically see a device like this and hold it. It is extremely heavy, and actually, even though the picture looks a bit small, it is quite large in real life. Okay. So coming back to how the data or the motion, the displacements are measured. The 2 points over here, this is where the fracture site is. These two, where there's the break in it, the top and the bottom we have, those 2 points are referred to as the one being the proximal bone segment and the one being the distal bone segment. So based on these two, we consider a motion of displacement. And the actual calculation of that displacement is based from a reference position. So without any load placed on this device, we will have that it sits exactly as it is. But as soon as any amount of load or strain is placed onto the external fixator, so if we think of it, you have it placed on a bone. As soon as you try and stand on that leg or something of that form, you're going to have some form of movement that takes place. And from the reference position, we will have that there is a slight motion that this external fixator experiences. And this will cause these proximal and distal ends to shift slightly. Now, there are 6 ways in which we consider the movement from the reference position to the reflected position, or the deflected position, apologies. There are 3 sort of translational movements that we experience. So from the reference position to the deflected position, we either have a movement in the x-axis, y-axis, or z-axis. So that's of a specific magnitude, right? So we call it a translational movement in the x-axis, y-axis, and z-axis. And then we can also see that based on the reference position, we also have a bit of a rotational movement that is experienced. So again, with regards to the rotational movement, we have a rotation about the x-axis, about the y-axis, and about the z-axis. So that gives us in total 6 different types of variables that we consider that make up this displacement that is experienced by this device. Okay. So for the data that we have then based on this, as I mentioned, the 3 rotational, the 3 translational movements, we have a sample of 80 data observations. These data points were obtained by considering different loads placed onto the external fixator, as well as loads removed from the external fixator, to see how the device sort of, in a way, contracts or compresses and decompresses, and how that strain and load of the decompression and compression actually affects the displacement and the motion that is being experienced by the device. Within the study as well, we consider the same manufacturer and a specific type of external fixator. And for this, we consider two different constructions. So in terms of the way in which these wires and pins are formed or are configured for the external fixator, we consider two different configurations, the same manufacturer and the exact same external fixator itself. Okay. We will refer to these different constructs as configuration 1 and 2 during the applications. Right. So now that we have an idea of what it is we're trying to model and the type of data we have, the first step was to go and see, okay, what is the best way in which all of these variables have been modeled previously? And during our research in the literature, we came across two specific assumptions where we felt that we could add a little bit of value from a statistical viewpoint. The first assumption is the assumption of independence. So previous studies that considered the stability of these devices assume that we have these 6 variables of displacement, informing displacement, and all 6 of them are independent. And they considered them in isolation and looked at what happens to the displacement about the x-axis, y-axis, and sort of use that to form a story. From a statistical point of view, we were like, okay, why not consider some form of dependent structure? We know that we have these 6 variables, and the intuition behind the way in which the physical model looks and the way in which these values are recorded brings about the idea that there should be some dependency. If a load is placed and we have that the motion of the displacement moves in an x-axis, then we feel like there should be some relation to how much displacement is in the y-axis as well, given the amount of strain, etc. So before we just go and jump in and say, okay, well, we need to consider dependence, the question arises, do we actually need it based on the data? So we did a quick study of the correlation within the data that we had, and this is just the correlation plot for configuration 2. Configuration 1 looks quite similar, and we can see that, yes, maybe not all the variables. So we have X, Y, and Z, and then the rotational variables. Not all the variables, however, there definitely is some dependence between some of the variables, and it is significant as well. So we do need to consider a dependent structure. The second assumption that we felt was a little bit overlooked was the cyclicity of the rotational variables. So again, besides the assumption of dependence, the assumption that all 6 variables are linear in nature is considered in other studies, and this violates the cyclicity or the periodicity that is observed within the rotational variables, so 3 of the displacement variables that we have. Okay, and this brings us to what we describe in the world or subfield of statistics as directional statistics. So what is directional statistics? Directional statistics is when we have any observation or variable that has some sort of periodic phenomena. So something like wind direction or time of day or the direction that an animal moves in. There are various other examples as well. Because of the inherent cyclic nature that these variables have, it's important that we consider their periodicity when modeling them. Okay. There are many different manifolds that we can consider within directional statistics, depending on the type of observations that we have, as well as the dimensionality. And usually if we consider a univariate case, so a single direction that we observe, we will have that these observations sit on the circumference of a unit circle. If we have higher dimensions, so if we have bivariate data, we can consider, for example, the sphere or the torus. And for circular and linear data, when we consider a mixed or a joint model for these 2 types of variables, we have what we call a cylindrical manifold. Okay. Now the question comes in, okay, great, there is the subfield in statistics, but do we actually need it? yes, we're saying there's periodicity that we need to account for in the cyclic behavior, but does it actually influence our end result? And the most simplest example that I'm going to use to motivate why we need to consider directional statistics is that of the descriptive measure of a mean. So we all know the mean, it's a popular measure in maths. And if we consider directional observations and we consider an arithmetic mean, where we just take the sum of the observations divided by the total values, the total number, if we consider our directional manifold, so we consider a circle, univariate, we have two observations. We're going to work in radians over here. So we have pi over 6 and 2 pi minus pi over 6. If we take the arithmetic mean of these 2 points, we're going to end up with the value of pi. So we're going to say that even though these 2 points are sitting here so close to each other, their mean is on the exact opposite side of the circle. Okay, intuitively from the diagram, we would expect that the mean be closer or between these two observed points. Right, so clearly the arithmetic mean is not giving us a true representation of where these 2 points lie on the circle, considering the fact that the start point and the end point, or 0 and 2 pi, are essentially the same value or same point on the circle. So considering that the beginning sort of coincides with the end of the domain or the boundary in which we are working with these variables, we need to consider adaptive methods. So if we consider the circular mean direction to better explain what's happening between these observations, we can see that by computing the circular mean direction, we actually obtain the true mean direction to be 0, which sort of fits in more with the intuitive idea around this data that we're working with. Okay. Just to put what we said regarding the periodicity and cyclicity more into mathematical statistical terms, what that means when we're working with the models or the probability models for directional variables, it means that if we have a random variable theta, which we're saying is a directional variable, and it has some distribution function that is a circular distribution function, then we know that the variable will lie in the interval of 0 to 2 pi, or it could even be negative pi to pi. So any sort of domain of 2 pi can be considered for a circular variable. And the periodicity element of it essentially tells us that if we take the angle, if we take the density function and we evaluate it at theta plus 2k pi for k being an integer, then we have that it's equal to the density evaluated at theta. Okay, the same thing for the CDF as well. Now, the interesting part with the directional statistics comes in the properties regarding the CDF, in that we have a point of discontinuity. Since our beginning of our circle coincides with the end of the circle, what we observe with the CDF, which differs from our linear domain, is that the CDF will equal 1 as theta tends to the boundary of the domain. However, if we evaluate the CDF at the points of the boundary, they actually equal to 0, since 2 pi is equal to 0 essentially. Right, so this discontinuity needs to be accounted for when we consider modeling techniques. And because of this, we do need to consider the directional model for these rotational variables. In this study, the two directional statistics distributions that we're going to consider are the CoE-MaSS distribution, or the circular normal. It is a very popular distribution in directional statistics. It has the same properties as the normal distribution, and it is quite nice in terms, or both of these distributions are quite nice in terms of their interpretable parameters. And then the second distribution is the Rapp-Cauchy distribution. Wrapping in directional statistics is, the easiest way I like to describe it is if you have a string and you hold on to the one end and you take it and you sort of wrap it around a unit circle until you get to the end of the string. And then you have a circular distribution essentially. So the Rapp-Cauchy, as it says in the name, it's essentially the Cauchy distribution that we've taken and wrapped around a unit circle to obtain a circular version of the distribution. In both cases, we have two parameters, mu being our direction, our mean direction, and kappa being a concentration parameter. Okay. So where do we start now? Okay, so now that we know we want to address the two main assumptions, one being a dependent structure, the second being we want to account for the cyclicity of these rotation variables. Essentially what we want is we want a multivariate joint circular linear model where we have some dependency accounted for. Right. So essentially that didn't seem like a tall order until we started having a look at some of the literature, and we realized that there are some limitations in that at the moment there's only bivariate circular linear models that can account for a dependency structure. So this doesn't help us that much since we know we have 6 variables, so we needed to consider another approach. So one of the ideas that came up, or a natural sort of methodology and technique in statistics, is, okay, how about making use of a copula? So we know we have these 6 variables, we know we can define distributions for them, so what about considering a copula approach? Now, we know in the linear world that there are many multivariate copulas that exist, and they can be easily applied to an application such as this. So the first step was to say, okay, well, can we just make use of these known methods directly for these 6 variables? And again, our periodicity requirement for the rotational variables poses a problem. So we cannot make use of the known multivariate copulas that exist because of the 3 rotational variables. The periodicity of these that we need to consider in the copula function as well, considering the rotational variables, have certain restrictions that our linear copulas that we have, or so-called, that I'm going to refer to as linear copulas, cannot account for naturally. So copulas in the directional statistics do exist if we consider a copula function for 2 circular variables. Jones and friends term the word circulars as the function that we make use of. However, again, the literature is limited. So we only have circular linear copulas in the bivariate setting, so for a single pair of a circular and a linear variable. And for circular variables, again, we limited to, or at the time of the study when we started, we were limited to a bivariate copula. Recently, earlier this year, there was a wonderful article on a trivariate circular copula for 3. However, again, that still poses a problem for us, considering that we have 6 variables at the end of the day. So we still need to account for all of them together. So then came the next idea. Okay, how can we consider another approach to develop this modeling framework? And then that's when the idea of saying, okay, wait a second, we can still make use of copulas, but what if we consider instead a pair decomposition of these copulas? And that leads us to what we refer to as Vine copulas. So we were able to then consider a modeling framework, and we'll see that it's quite a nice general modeling framework that we've proposed here for circular and linear data based on Vine copulas. And the idea was inspired from a paper by Wang et al., which considered a meteorological example where they had 3 variables, 2 being linear and 1 being circular, and they made use of this pair decomposition approach to build this multivariate joint model with a dependent structure. Okay, so how does that look for us? There are many types of Vine copulas. The one that we're going to focus on and the one that we've applied in this study is the canonical Vine structure. So this allows us to sort of break down the pair decompositions in a nice visual illustration of a tree-based structure. And from this tree-based structure, we're going to consider various pairs. And based on these pairs, we will develop our full model. Okay, now with the canonical Vine structure, this is just one of the possible structures that can be considered for the model, different sort of tree structures for these 6 variables will lead to different models. So it's very important that in this step, you could pay careful attention to how it is you decide which variables are going to be related to each other, and what do you consider as what I will call the main or trigger variable, essentially. So this structure was then defined based on many discussions with our domain experts as well. And we came to the conclusion to use this specific structure with Z being our main or trigger variable. And the reason being for that, Z is sort of the translational movement in the Z axis. So sort of an up and down, you can think of it. And the way it makes sense to think of it, but I know the terminology is not right from our clinician and engineer. They will kill me for saying it, but the Z sort of is like the compression and the decompression, right? The up and down movement. So only when a load is placed onto this device and you experience some sort of compression or decompression, will you have some motion of displacement being observed. So that was the motivation for Z being our main variable. And then we just had Z being connected to each of the other 5 variables. From there, we're going to now consider the pairwise copula for each of these little tree branches. And we will consider a sort of a pairwise copula function for each tree branch until we reach the end of our tree structure, in terms of there's no further linkages between any of the pair sets of variables, if I can say it that way. And from this structure, we can then extract how our final model looks like. So the nice thing about vine copulas is we can actually get a form for our PDF. So from the trees, using Scarlett's theorem, so again, we're back into the copula world. It's simply the marginal times the copula function. And instead of considering one multivariate copula, we consider the pairwise decomposition copulas. So each of these copulas are the pair copulas that we've obtained from the tree branches that we had in the previous slide. Now, as we can see, this is quite a nested function, and it relies again a lot on the conditional variables. So if we go back to the tree as well, we can see that once we get to the sort of the second tree, going to the third tree, when we consider the relationships of the branches, we have these conditional relationships that keep building on. So the wonderful thing about vine copulas is it's a sort of an easy method of breaking down a complex multivariate problem into simple bivariate pairs. However, we can see that as the dimensionality of this increases, the structure of our vine copula becomes extremely complex. Right. Okay, so considering now that this is our PDF, the next step is to say, okay, well, we have this form, we can go and model our data. Then before we jumped into the actual application of this model, we went and looked at the data a little bit more. And we realized that, wait a second, our variables are not necessarily, or the data itself is not necessarily displaying unimodal behavior. Some of the variables, yes, but not all of them. We do have some form of bimodality. So this is the translational variables, and I'm only showing 2 of them, X and Y in this case, for configuration 1. Our Z variable, and for configuration 2, we see a similar behavior in terms of multimodality being observed. For our rotational variables as well, we can see quite nicely here for the rotational of X and Y. We can see with X, we have a nice bimodal looking distribution, and Y is nice and unimodal. So we do need to account for this somewhere in the model as well, in that right. So how do we account for this multimodality that we've observed? The easiest way, or the way in which we've considered, is by making use of a finite mixture model. Finite mixture models is an easy way of building a multimodal distribution with specified unimodal parts, essentially, and we weight this function. In the application, just considering the complexity of the PDF, where we have these multiple conditional copular functions being fed in, we're going to consider a maximum of 2 clusters or 2 mixture models components. Okay. So this now accounts nicely for the multimodality that we're observing. There weren't any other behavior that we deemed necessary to consider different modeling approaches for. And then now we can move on to actually defining the marginal distributions and copular functions for our model. So just to keep things simple as a first step, as in previous studies, when the variables were considered independent, the assumption of normality for these variables were considered. So we decided to at least keep some of the assumptions a little bit the same standard, just so that we have some form of safety with regards to any new implementations that we're adding on. So for the linear variables, we consider the normal distribution, and in certain cases, a mixture or a 2-component mixture of a normal distribution. And then for the circular variables, in this application, we've considered the Rab-Cauchy, simply because it handles highly concentrated data quite well, which is what we've observed in some of the variables that we have here. For our copular functions, for the linear copular function, which we denote as LL, we've considered the Farley-Gumbel-Morgenstern family. It's quite a popular family of copulars, and one of the reasons being is that it has some easy algebraic features, which we take advantage of. It has a nice simple function, and it's a 1-parameter copular, which makes it quite nice to work with in our case. For the circular linear copular, the most popular circular linear copular was proposed by Johnson and Wiley in 1978. And they proposed the copular form as given here in equation 4. And this G function here simply results in a circular PDF, where we have the argument being a function of a parameter Q, which can either be 1 or -1, depending on our correlation. Do we have negative or positive correlation or dependence that is being observed in the variables? For our circular copular, or our circulars, as Jones termed it, the model proposed by Jones in 2015 follows a very similar approach to the Johnson and Wiley copular. And again, it results in a circular PDF where we have an argument looking exactly like equation 5. Okay. Definitely, further considerations, you can consider various other combinations of marginal distributions as well as copular functions. For this study, we've just limited it to the following for easier computation. Okay, so now that we've defined our marginals and our copular functions, the next question comes in is, are we going to estimate this entire density as given here? Considering the fact that we only have 80 observations, we can imagine how complex and how many parameters this will require. So under the practical considerations that we had, we decided to consider a truncated version of our Vine copular model. So Kuruika and Bregman proposed the idea of truncation with regards to Vine copulars, especially when going within high dimensions. And the idea behind the truncation is that any additional information that is sitting sort of within the higher dimension or the higher trees within this copular function is not significant enough to contribute towards the final model, and instead just increases the computational complexity with which we're dealing with. There are various ways in which you can choose the optimal truncation point, and many studies investigate where do you choose a cutoff point. For this study, we didn't go with an optimal cutoff point. Instead, we considered a more pragmatic approach for computational efficiency, for practical implications. And as we mentioned, we only have 80 observations. So considering the small data size, sample size that we're working with, we considered to truncate at tree 2. Okay, so considering our truncated vine copula model, considering our marginal distributions being normal for the translational variables and Rab-Cauchy for the circular, or if we have the MN here in this table, it refers to a mixture of normal distributions, or a MWC is a mixture of Rab-Cauchy, and in this case, it will be a two-component mixture. For each of these, we consider two different cases for each configuration. So I mentioned in the beginning, our data, we had two different constructs of this external fixator, configuration 1 and configuration 2. And for each of them, we've considered two cases over here. Case A1 and A2 are sort of the, if I can say, the more simple case. So we're not considering any mixture models in here. We just consider normal distributions for the translational, Rab-Cauchy for the rotational variables. Within our copula functions for the circular PDF, again, we've considered the von Mises. And a full study, we've also considered we've considered Rab-Cauchy, sorry. Within the full study, we've also considered von Mises distribution for the circular PDF of the copula function, just to see how it performs and compares. Based on our results, we can see that for configuration 1, the slightly simpler model, in terms of no mixture components, actually performs better. And for configuration 2, we have that the more complex form where we have a mixed Rab-Cauchy for the the rotational variable about the z-axis, as well as then a mixture of normal distributions for the translation about the y-axis, actually performs much better. Okay, so we have now our model, but now the question comes in, coming back to our assumptions, and the research question that we had is, okay, for the cyclicity of the variables, we've motivated that from the theoretical point of view by explaining why directional statistics is important, why we need to account for periodicity, etc. But coming back to the first assumption that we wanted to address in the study is the assumption of independence. So is there validity, or is there a reason why we should consider a dependent structure for this model? So just to emphasize or sort of reevaluate and validate the necessity for this dependent structure, we considered a likelihood ratio test, where we considered an independent model versus our complex model. So for the independent model, what we've done is we've considered X, Y, and Z, theta X, theta Y, theta Z, as we've given in this table. And essentially all of these copulas we've considered as independent copulas. So essentially we remove them, and our joint density is simply just the product of the marginals. And our alternative hypothesis is the complex model. So in this case, we've chosen the more complex cases of B1 and B2. So where we have the mixture components in, just to sort of test the extreme case in this case of high complexity versus just the product of the marginals, independent assumption. And for both configuration 1 and configuration 2, we see that our dependent structure, even though it is so much more complex than an independent model, actually does show to be valuable and significant within this application. Okay. To conclude, one of the things I really like about this modeling framework that we've proposed is the flexibility that it allows the practitioner or the researcher. So for the application, we've considered specific copula functions, we've considered specific marginal distributions, and we've also considered a specific tree structure or vine copula structure in terms of the canonical form. However, the general framework can be extended and adapted to various other assumptions. So we can consider a whole list, it's almost limitless list of combinations of marginal distributions and copula functions. And we can also play around with the dependent structure that we would like, or that is desired based on the application that we're interested in with regards to the vine structure that we propose. So that's essentially where we ended off in this study. We were quite lucky during the course of the study to obtain some financial support, so we're grateful to our funders for this project. And then just some of the main references with regards to the idea behind vine copulas, our famous Johnson and Wiley copula, which is widely used in directional statistics, our circular copula, and then just where we got the original idea from as well. Thank you.
Thank you, Priyanka, for an interesting talk. Are there questions from the audience?
Priyanka, can you hear me?
Yes, Prof.
Just a basic question on directional data. The whole idea of how good is the fit, you assume either the von Mises or this RAP Cauchy. Is there any way of testing a kind of goodness of fit, or how well are you doing, or how sensitive is what you're doing with respect to your distributional assumption?
Yes, within directional statistics, there are a few measures on sort of when we have the model here. So there is some goodness of fit tests that or have been developed for directional statistics models specifically. With regards to the most popular in literature, the BIC and the AIC is used still till date for model comparison. But in this case, we didn't, we just based on we did do a marginal analysis at first for the individual distributions where we had, where we considered each variable in isolation, and that's also how we got to the von Mises and the RAP Cauchy distribution. Yes.
Okay, thank you.
Actually, I do have a question.
There's a question from the live audience here.
I don't know, can she hear me, Priyanka?
Sorry?
Oh, where's the microphone in this place? Can you hear me now? Is it a bit better?
Yeah, it's a bit better. Thanks.
Okay, great. In the model, you said that when any load is applied, there's some type of deformation and there's like a shift, right?
Yes.
Okay, so
Yes.
my question is kind of twofold. I'm assuming that there's some threshold, that anything below that threshold, there'll be no movement. So like for very light loads, nothing will change. And then past a certain type of load, then things start shifting.
Yes.
Okay, so does that mean that using the statistical techniques, you could estimate how much load could be applied to a fracture before something shifts?
So in this application, we didn't actually consider the amount of load that was placed on. So the data that was collected was I should have probably mentioned this, apologies, is we had a sort of a simulated virtual environment. So as in this image over here, this is actually the simulated virtual environment. We had this device fixed onto this system, and essentially it sort of imitated the different loads being placed on, and then recorded the displacement that occurred. So we didn't actually consider any function of the amount of load placed itself. We just considered a function of the actual displacement observed.
But surely the displacement is related to the load. Surely it's coupled. So a heavier load would result in more displacement, surely.
Yes, that is a general idea, but with the sort of the aim of the study was not to sort of determine how do I say it? The actual amount of load, it wasn't related to the amount of load, it was just related to how the displacement or sort of what type of displacement is observed. So the device is there's not only load placed on the device, but there's also loads being removed from a specific point. So there's the decompression and the compression that happens as well. So if you have, for example, a load of, let's say 10, whatever 10 is supposed to be, you have a load of 10 placed on, and you build it up. So let's say you place a load of 10 and then you place another load of 10. So you have a total load of 20, right? And at each loading set time, you record the displacement. When you unload 10, so you have 20 and now you're unloading 10 again, you still have a load of 10, but your displacement is different because of the compression and the decompression effect, if that makes sense.
Okay, so I get it. So you were more interested in the shifts, the rotation, and everything else.
Yes.
Rather than actually looking at the load itself.
Yes.
Okay, perfect.
Yes.
Because I think that could be quite cool. Like if somebody has a fracture in a bone and you take an X-ray and you could estimate that they could put like 1/5 of their body weight on the leg without damaging it further. That could be quite interesting to look at.
Definitely, but the idea with the external fixator, the device specific that we considered, when they place it or fix it on around the fracture or whatever, it sort of forces immobilization. So the idea is that if you have this placed on your leg, for example, if you've broken your leg, you shouldn't get up and walk on it. Yes.
Thank you. Are there further questions for Priyanka? There's something in the chat there. Oh. Let's see it. One of your chatters is complimenting you on your work.
Thank you.
I will leave that. Then thank you, Priyanka.